So our goal in this video here is to derive the mean and variance formulas for a binomial distribution. Deriving mu, and well, really we're looking for sigma, I guess, standard deviation. Sigma squared would be the variance for a binomial distribution, or maybe a binomial random variable. So this is our goal here. To do that, we need a couple of pieces. One is for any probability distribution, discrete probability distribution, mu, or mean, is really the sum of sort of x times the probability of x. So we're going to just calculate this formula, essentially, is what we're going to do. And the variance here would be the sum of x minus mu squared times the probability of x. So these are two formulas. This one does the mean, this one does the variance. Note the mean shows up in the variance formula here, so we have to do the mean first. It's simpler typically anyway. And then once we have sigma squared, our standard deviation is just the square root of the variance, which makes sense. Square root of a square should cancel out. Okay, so now what we need also is that for binomial, so if we have a binomial distribution, P of k, the probability of k successes, if we're doing n trials, this would be n choose k, p to the k, and then we get a 1 minus p, or sometimes that's written as q, to the n minus k. So p is our probability of success. Here, note this p over here is a probability of function. It's different than the p over here. So this is a probability of success. And then k is the number of successes, n is the number of trials here. And then we want to say the k's that make sense is that k here that we can do are 0, 1, 2. We could have anywhere from 0 up to really n successes. All those whole numbers. Okay, so we're going to just put this together and just calculate these things out. Couple facts that we'll need here. We'll probably have to get other videos to establish two of these. One of these we're going to assume that perhaps you've seen, you can probably look at in other places. But we're going to use some summation facts here. These are just equations that are just true. Now the first one, and this is one you may well have seen before, this is k equals 0 to n choose k, x to the k. You add that up, you get 1 plus x to the n. So this is a version of, or maybe it is the, so this one is called the binomial theorem. That's the binomial theorem. Here, that's well known. You may have seen that in some kind of an algebra class. What's less known, and very related here, if you do k equals 0 to n, if we put a k in front here, so we do the same n choose k, x to the k, but we multiply by a k as well. This is our indexing variable. What you get, something kind of like this, but a little bit different. This is nx times 1 plus x to the n minus 1. We'll get another video to sort of establish this. It's going to require, well, you can do it directly in this case, but there's a more general principle that requires just a little bit of calculus. We'll probably do both of those. A related fact that we'll need as well is if you do k equals 0 to n, k squared, n choose k, x to the k. So instead of a k, you put a k squared. Then what you get is nx times 1 plus nx times 1 plus x to the n minus 2. So it's getting more complicated as the sort of formulas, as this power on k increases. You could view this as a 1 here, which is a k to the 0, perhaps. But you get some other formula, and we can sort of derive that using some general principles in calculus, or just sort of directly as well. Okay, so those are our key facts that we'll use. There'll be places where those will pop up. So let's start off with mu. So our mean here, and again, that was the sum of x times p of x, probability of x, which for binomials here, the possible x's are 0 to n. So the way we'll write that is k equals 0 to n. So this means do k equals 0, and then k equals 1, k equals 2, k equals 3, and you add those up. That's k equals 0, 1, 2, 3 of whatever we put here. X, well, that's k, so that's the variable. And then we get the probability of getting k successes, and that was the binomial distribution formula, which is n choose k, p to the k, 1 minus p to the k. So this is really what we're trying to find here for mu. You may already sort of know what mu is or be able to guess that for this distribution here, but we want to sort of derive this mathematically just to show that we can get some idea of what's going on sort of behind the scenes. Okay, so what we're going to do here is I'm going to rewrite this sum to make use of this second sort of identity here. So I'm looking for k times n to the k times x that is something to the k. So I've already got my k, n to the k. I need to sort of write this, second part as something to the k, but I'm noticing I made a mistake here. This isn't 1 minus p to the k, it's 1 minus p to the n minus k. So that was really our formula. It should always just have an n minus k. That was just a mistake on my part. Okay, so again, we have k times n choose k, and we want to write this as something to the k. So to do that, what we're going to do is I'm going to keep everything at the beginning the same, and choose k p to the k, but this 1 minus p to the n minus k, I can rewrite that as 1 minus p to the n over 1 minus p to the k. Okay, and then there's just a general property of these summations. This 1 minus p to the n, that's a factor of this thing on the inside, and there's no k at all. So what that means is I can pull that out of my summation. Effectively here, I'm factoring out a 1 minus p to the n from every term that I'm adding together here. In essence, just go to the side, this is essentially very similar to if you had, say, 2x plus 4, that this would be 2 times x plus 2. You're like factoring a 2 out of each term here. Essentially, that's what you're doing here with a 1 minus p to the n. Okay, so you get the 1 minus p to the n, and then we get our summation, k equals 0 to the n. We have our k, n choose k, and now I have p to the k over 1 minus p to the k. Well, those will combine to p over 1 minus p to the k. And so now I can use this formula up here. Whoops, we see both of these here. So we have k, n choose k, x to the k. So if I let x be this p over 1 minus p, I actually fit this formula exactly. So let's use that. So it's nx. I keep my 1 minus p to the n. I get n. X was p over 1 minus p. And then I have 1 plus x to the n minus 1. So I get 1 plus p over 1 minus p to the n minus 1. So that's our formula here. And you'll note the key thing here is we got rid of the summation. So this would be called really a closed form formula. And we just want to simplify this down now. To do that, let's just work on this here. I'm going to work on this thing in here first. So what I'm going to get is 1 minus p to the n times n. We get a p. Let's see, we have a 1 minus p in a denominator. And then that's the p over 1 minus p. And then this, let's see, this is 1 minus p plus p over 1 minus p. So the 1 I can rewrite as 1 minus p over 1 minus p. So I get 1 minus p plus p to the n minus 1. Let's see, here I have, well, I can cancel one of these 1 minus p factors with the 1 minus p factor in the bottom. Give me 1 minus p to the n minus 1, n times p. Here, minus p plus p cancels. I just get 1 over 1 minus p to the n minus 1. And then what I'm going to get is 1 minus p to the n minus 1 times np times 1 to the n minus 1, which is just 1, over 1 minus p to the n minus 1. And you'll note that these will cancel, and I'm left with my mean, mu. This is np, which is the formula we should expect really for a binomial distribution with n trials and p as a probability of success. Okay. Next one, we want to work on really getting our standard deviation, and our strategy here is to find the variance first and then just take the square root of that. This is a pretty common strategy for finding a standard deviation. So what we're going to get, our variance formula for any discrete random variable is this is x minus mu squared times the probability of x. And you just add those up for each x here. And so in the case of the binomial distribution, this is sum k equals 0 to n. This is k minus mu, except for mu, we know that mu is np squared. And then the probability of getting a k here, that's going to be n choose k, p to the k, times 1 minus p to the n minus k. So again, we just get this summation here, and now we want to evaluate this or simplify this down, and particularly want a closed form. I'm going to move this over here just for more space here. And so first thing I'm going to do is, just like before, I'm going to pull out a 1 minus p to the n from this outside of the summation. And then I'm going to get k equals 0 to n. Now I'm going to sort of expand out this k minus np squared. So that's k squared minus 2 npk plus np squared is n squared p squared. And I keep my n choose k, and then I have p to the k. I already pulled out the 1 minus p to the n. I still have 1 minus p to the negative k. Putting that together with the p to the k is going to give me p over 1 minus p to the k. Okay, so now what I'm going to do is, this looks very much like the formulas we had before. It was n choose k times x to the k, but then sometimes we had a constant, really nothing out there, which is a 1. Sometimes we had a k, sometimes we had a k squared. What I'm going to do is distribute this and split this into 3 sums, where here's really our k squared, here's our k, here's our 1, really. So what I'm going to get here is 1 minus p to the n, and then times the k squared times this will give me k equals 0 to the n, k squared, n choose k, p over 1 minus p to the k, minus, and then the 2np times the sum k equals 0 to n, k here, times this stuff here, which is n choose k, p over 1 minus p to the k. And finally, we have the n squared p squared from here, multiplied by the sum k equals 0 to n, just n choose k, p over 1 minus p to the k. So we work all that out as we go along. Okay, and then we gotta keep going here. I'm gonna flip down to another page, get some more space here. So what I'm gonna get now, let's say we just gotta work these things down. 1 minus p to the n, and now the formula for k squared, n choose k, x to the k. So let me just go up and find that. It's way up here. So it's this formula here. So it's nx times 1 plus nx times 1 plus x to the n minus 2. Just maybe write that up here. That was nx times 1 plus nx times 1 plus x to the n minus 2. That's really going to be this thing here, except x is p over 1 minus p. So if we apply that, we get n times x is p over 1 minus p times 1 plus n times p over 1 minus p times 1 plus p over 1 minus p to the n minus 2. Okay, that's really our summation with the k squared. Minus 2np, summation with the k. If we go up here again, that formula, it's nx times 1 plus x to the n minus 1. Just write that here, nx times 1 plus x to the n minus 1. That should be the summation here, but x is p over 1 minus p to the k. So what we get is times, so the 2np was out in front, n p over 1 minus p, so nx, and then we have to get 1 plus p over 1 minus p to the n minus 1. And then our last term here is n squared p squared, and this one was the one that's just 1 plus x, which is p over 1 minus p to the n. We close our bracket here. So we get this big sort of ugly thing here, and we're going to try and simplify this down now. But the nice thing here is we got rid of all the summations. This is a closed form now. So it's particularly not simplified yet. It'll look a lot nicer here in a bit. Okay, so this is 1 minus p to the n. Over here, let's see, I'm going to do n times p over 1 minus p from these first two factors. Here I can do a, let's see, 1 minus p from the 1 is 1 minus p over 1 minus p plus np over 1 minus p. This, I get 1 minus p plus p. Let's just write it out again. 1 minus p plus p over 1 minus p. Note that top is going to be 1 to the n minus 2. Next bit, we have 2. Let's see, we have n times n, that's n squared. We have p times p here, that's p squared. We have a 1 minus p in the denominator for this guy. And then this, sort of to the n minus 1 bit, that's going to give us 1 minus p plus p over 1 minus p to the n minus 1. And finally, we have our n squared p squared. Same thing, 1 minus p. 1 is 1 minus p over 1 minus p plus p over 1 minus p to the n. Alright, so we get 1 minus p to the n. We get np. So what I'm going to do here is I'm actually going to distribute this np times the 1 minus p plus np. So I get np minus np squared plus n squared p squared. This is all over 1 minus p times 1 minus p is 1 minus p squared. This other factor here, this is going to be a 1 to the n minus 2. That's still 1. And our denominator is 1 minus p to the n minus 2. Next term here is 2n squared p squared over 1 minus p times 1 minus p plus p is 1. And then I have 1 minus p to the n minus 1 plus n squared p squared times, we get a 1 to the n is just 1 over 1 minus p to the n. Okay, now, maybe it doesn't look so much better yet, but nice things are going to happen. I can distribute this 1 minus p to the n to each of these three terms here. And what's going to happen is that's just going to completely cancel the denominators in all three. So this is a 1 minus p squared, and then n minus 2 more 1 minus p's. So together there's n factors of 1 minus p. Here's one factor of 1 minus p, and n minus 1 more. N minus 1 plus 1 would give me n factors of 1 minus p. And then I have 1 minus p to the n. So what's going to happen here is this is going to cancel with those two on this term, with those two in the middle term, and just with that on the third term. And after we do that, what we're left with then is just np minus np squared plus n squared p squared here. Here we have minus 2n squared p squared. And then we have plus n squared p squared from the last term. And then some nice things happen here. Again, we have a plus n squared p squared plus 2n squared p squared, but then minus 2n squared p squared. So these three cancel out. And then with these two, we can factor out an np, and we're left with 1 minus p. And so this is our variance. Now, a lot of times this will be written as n times p, and that 1 minus p is q. So that's our variance. Our standard deviation is the square root of n times p times 1 minus p, which can be written also as n times p times q, square root of that. Okay, so there's our derivation of the standard deviation and the mean of a binomial distribution. This is the kind of thing you really only want to do sort of once and then reuse that, because I mean it's a lot of work for a pretty simple looking result here. We've got a few things to kind of show yet here, really, where I kind of said, oh, just trust me on these facts here, but we can get other videos to show you how those work.